Welcome everyone. In this lecture, we'll be talking about central tendency and variability. So these are chapters 3 and 4, respectively, in your textbook. We'll see if we can get through the whole lecture, this whole presentation as one. If I see that I'm going on a little too long, we'll just break them up into two separate pieces. One that deals specifically with central tendency, and the other one that will deal with variability. Okay, so what will we be talking about? Well, the topics that we'll discuss will include the mode, the median, the mean, variability, range, variance, standard deviation, and z-scores. So let's start by talking about what is central tendency. So a measure of central tendency is a score that indicates where the center of a distribution tends to be located. So this is where the tendency comes from and the central part of central tendency. So where in the distribution, or where the center of the distribution tends to be located. So it is a score around which most of the other scores are going to be located, and it will provide a reasonably accurate estimate of the distribution as a whole. We'll see in a moment here there are three major measures of central tendency, and some are better than others, let's say. So the three measures of central tendency are the mode, the median, and the mean. Okay, so what exactly is the mode? Well, the mode is simply the score that appears most frequently in your distribution. So let's use this distribution of scores here as an example. You see we have 1, 1, looks like 3 2s, 2 3s, a 4, 2 5s, and a 6. In this case, we see that 2 is the score that appears most frequently. So the mode for this distribution would be 2. Pretty easy, right? So when a distribution of scores only has one mode, we call that distribution unimodal. This would be an example. Actually, this is the histogram of the distribution that we just used as an example. And we could see the mode is the score that appears most frequently, the score with the highest frequency in that distribution. Okay, sometimes a distribution will have more than one mode, though. So let's take a look at this distribution as an example. In this case, we have 1 1. We have 3 2s, 2 3s, a 4, 3 5s, and a 6. So the mode would be 2. That appears 3 times. But we have another score that appears 3 times as well. 5. So in this case, the mode would be 2 and 5. So when a distribution has more than 2 modes, well, when a distribution has 2 modes, we call it bimodal. A distribution can actually have more than 2 modes, and in that case, we would just call it a multimodal distribution. But here's our distribution graphed as a histogram, and we can see clearly the two scores that appear most frequently, 2 and 5. So these are the two modes of our distribution. Okay, now there are some issues that arise when using the mode as a measure of central tendency. Again, the goal of central tendency is to give us an idea of where the middle of the distribution might be. Okay, so keep that in mind once we discuss each of these issues here. So with more than 2 modes, we may fail to adequately describe our data. I would say even with a mode or mode by itself might not adequately describe our data, but let's stick to the slides here. Also, it's possible to have no mode. In other words, there might be no score that is more frequent than others. You literally might have a distribution of values that occur all at the same frequency. Third, the mode only tells us which score occurs most frequently. It doesn't tell us anything about any of the other scores that are in that distribution. So, the mode is typically used to describe central tendency when the scores reflect a nominal scale of measurement. For example, when participants are categorized using some type of qualitative variable. So if we were dealing with nominal data, if we were dealing with groups of participants, we might use the mode as a measure of central tendency because it's going to tell us which group is occurring most frequently, or which group has the most number of scores or the most number of participants in it. Other than that, using the mode for a continuous variable is not going to be all that useful. So we have another measure of central tendency called the median. And this is a step up from the mode, but we'll see that it too has some problems. So what is the median? Well, it's simply the middlemost score, or what we would call the 50th percentile in a distribution, right? So it's the score that is right smack in the middle of your distribution. So let's take these exam scores as an example. So we can go through each of these. We see there's a range of scores in here, and there's an n of 11. So a total of 11 scores in this distribution. The first step is to list these scores, the scores that appear in this distribution, from lowest to highest. Right? So starting with the lowest score of 60 and listing them in order all the way up to our highest score of 98. Okay? The second step, if you have an odd number of scores, it's pretty easy. Just count up to the middle score. So if we have 11 scores in this particular distribution, we just count up to the score that appears smack dab in the middle, which is 72. So we would go up 60, 62, 65, 65, 65, 72. So there are an equal number of scores that occur above 72 in this distribution as there are the number of scores that occur or appear below 72 in our distribution. So the median is the middlemost score, also the 50th percentile. Okay, so we have a median of 72 in this case. When you have an odd number of scores, finding the median is pretty easy. When you have an even number of scores, it's still pretty easy. There's just one additional step that we need to do. So let's say we have an even number of scores in a distribution. There you go. Let's say these are exam scores. And we have a total of 12. So n equals 12. 12 exam scores. It's not an odd number, so there's not going to be a very clear middlemost score. So what are we going to do? Well, the average, we're essentially to calculate the median for a distribution that has an even number of scores, is that we're going to take the average or the mean of the two scores that are in the middle. So let's take a look at how that might work out. So these two scores, 65 and 72, are the middlemost scores. How do we know that? Well, remember that there's 12 scores in this distribution, right? So we could count. There's 1, 2, 3, 4, 5. And then after 72, there's 1, 2, 3, 4, 5. Right? So above these two scores, we have half of our distribution, and below these two scores, we have the other half of our distribution. So we know that these are the middlemost scores. So once we've identified the two scores that are smack in the middle. Again, this is after we have listed our scores out from highest or from lowest to highest. We will go ahead and get the mean of these two scores. So add those two middle scores together and simply divide by 2. And this is what is going to be our mean for this distribution. So in our case, we'll take 65, 72, add them together, divide by 2, and we get a median of 68.5. So in this case, the score of 68.5 is our middlemost score. It's the median. It's the score at which half of our distribution occurs above it, and the other half, or the other values, are below it. Okay? So again, just another step, but pretty easy one to calculate the median when you have an even number of scores in your distribution. Okay, so what are some of the problems that exist with the median? Well, first, the median might not provide a representative estimate of central tendency when the distribution is not unimodal or when it's not symmetrical, right? What does that mean? Well, let's take a look if we have some examples here. But another issue that might arise with using the median is that it only takes into account the frequency of scores above and below the 50th percentile. It does not take into account the numerical value of those scores. So are we really getting an accurate representation of our distribution using the median if we're not taking into account the values of the scores, if we're only looking at the frequency at which those scores occur? You're not guaranteed that, right? Another potential issue here is that, well, something to keep in mind when the median might be useful is when we need a measure of central tendency to describe data that is rank order or ordinal in scale. So think about the mode as being most useful when we have nominal or categorical data, and the median as being most useful when we have rank order or ordinal data. Okay, so in this class we're mostly going to be focusing on the mean, and the mean is the most common measure of central tendency that we use in behavioral research and psychological research, and hopefully you'll see why in a moment here. So it is a score that is located at the mathematical center of the distribution, not the physical center per se, right? But at the mathematical center. You might say, okay, what the hell does that mean? I'm gonna show you what that means in a second here. So the mean has the advantage of taking all the scores into account, and not just the frequency of each of the scores, but also the values of each of those scores. So the scores and their values are taken into account when calculating the mean, which is there to represent the distribution. So already, hopefully, you can see how the mean is different than the previous two measures of central tendency. One was literally just looking at which score occurs most frequently, the mode, right? The median was looking at, well, what is the middle score? Not paying attention to the values of the score that occur above or below that middle score. And here we have the mean that is taking all the scores into account, not just how many times they occur, but also their value, right? So already we're in a better place in terms of getting a number that is going to best represent all the scores that are in the distribution. So the mean is often referred to as the average in just common usage. So when we say, take the average of something or calculate the average of something, what we're really saying is calculate the mean or take the mean, because technically the mean, median, and mode are all forms of quote-unquote averages. They're all measures of central tendency, but the mean is, again, the most common in research, and it's also the most common measure that we use in daily life. So to compute the sample mean, pretty easy. I'm sure you've done this many times throughout your life. We simply sum up all the scores in our distribution and then divide by the total number of scores. So we're going to sum up all of our x scores, add up all of our x's, and then divide by n, right? So there you go. And you'll see mean represented in different ways or using different symbols. Here we're talking about a sample mean, so we're using the statistical symbol here called X bar, right? So it's just an italicized capital X with a line on top of it, X bar. When we start talking about the normal distribution, and once we start running some z-tests a couple weeks from now, we'll be dealing with a population mean, and that actually has a different symbol associated with it, something called mu, the Greek letter mu. But for now, let's just focus on what the mean is and how to calculate it. So for a sample mean, or x bar, we sum up our x's, sum up our scores, and divide by n, our total score. So, there you go. Was one step ahead. So when denoting the population mean, as I just said, we use the Greek symbol mu. And there you go. That's what it looks like. So any of you who are in Greek life might already be familiar with that, or if you've taken a statistics course before, or if you speak Greek, right? Okay, so let's calculate the mean with the following distribution of scores. So we'll pretend that these are some exam scores, and you see they look like they range from 60 to 98. So 60 is our lowest score, 98 is our highest score. So to calculate the mean for this distribution, we're going to sum the scores that appear in that distribution. So we take 98 and add 62, add 65, add 60, or add 98, add 97, 65, so on and so forth, right? We're just adding these values together. So that is our sum of, that's the sum of our x scores, right? 875. That's the sum of all the scores in our distribution here. The second step is to simply divide by the total number of scores that we have, which is n, right? So in our case, n is 11. We have 11 scores in that distribution. So we'll take 875, we'll divide by 11, and we end up with 79.55. So this is the mean for our distribution, 79.55. Okay? And if we take a look at this distribution, if we take a look at the individual scores in there, we can see that 79.55, just by eyeballing it, I would say is doing a pretty decent job at representing the middlemost, not the middlemost in the sense of median, but the mathematical center of this distribution. Okay, so what are some of the issues that come with using the mean? because nothing is perfect, right? Well, one of the issues is that the mean is sensitive to extreme scores. So let's take a look at this small distribution here. There's only 5 scores in there, and for this distribution, the mean is 10.4. But what happens if we added an extreme score? So let's add in 38 to this distribution. All the rest of those scores don't seem to vary that much, right? They tend to be pretty close together. The range there from highest or lowest to highest score is only 7 to 15. So those scores are kind of sticking together pretty nicely there. So then we throw in a value like 38. We're kind of throwing in an extreme score. That's kind of way out there. It's much more distance between, let's say, any other value in this distribution and this new score that we added. Okay, so in this case, our mean, just by adding 38, our mean is now 15. So you can see just adding one score that is high actually raised our mean by 4.5 points. So the mean can be deceptive in a sense, or less accurate, if we have a handful of extreme scores in either direction. If we threw, a large negative number in there, it would drag that mean down as well. Okay, so something to keep in mind. So the mean is typically used when as a measure of central tendency, when the scores reflect an interval or a ratio scale of measurement. And that's the scale that we're mostly going to be dealing with for the rest of the course, this interval ratio scale. Of course, they're 2 separate scales, but we often combine them. So for that reason, the mean is the measure of central tendency we're most often going to be using. Okay, so let me do a time check here. It's only half an hour, so let's go for it. Let's see if we can do this all in one go. So chapter 4 in your textbook talks about variability. So what is variability? Well, variability measures measures of variability, describe the extent to which scores in a distribution differ from one another. So in that last example, I said these scores all seem to be kind of sticking together. They don't seem to be too far apart. Doesn't seem to be too much distance between them. What I was really getting at is that this distribution seems to have low variability. It's not a whole lot of variability between the scores. Not a whole lot of distance there. They're all kind of sticking together. So you'll see in a moment we have a few measures of variability, just like we have a few measures of central tendency, and some are more useful than others. So without a measure of variability, a measure of central tendency, something like the mean, provides a pretty incomplete description of the distribution. And I'll give you an example here. So let's take a look at 3 different distributions that all have the same mean. So we have sample A. Take a look at that data. 0, 2, 6, 10, and 12. Then we have sample B, 8, 7, 6, 5, and 4. And then sample C, all 6s. All of these distributions have a mean of 6. But clearly, the scores in sample A are more different compared to the scores in sample B, and definitely compared to the scores in sample C, because the scores in sample C are exactly the same, right? So mean by itself kind of gives us a only half of the picture in terms of trying to describe a distribution, because all of these have a mean of 6, but they're very different distributions. Again, sample A has a lot more difference between those scores, a lot more distance between those scores. Sample B, the scores are more tightly together. And then, of course, sample C, the scores are exactly the same. So whenever we present a measure of central tendency, or whenever we present the mean, we should always present a measure of variability, and one measure in particular. But let's take a look at 3 measures of variability that we can use. The range is the most simplest, and not exactly the most informative. It's simply the highest score minus the lowest score. This would be the range, how you would calculate range. And we'll do examples of these. Variance is the sum of squares divided by the degrees of freedom, and we'll talk about what those mean, what those two terms mean in a moment. We'll calculate both of those, but you can see the mathematical formula here, and you can also see that this newer version of PowerPoint doesn't like my old formatting in these slides here. But this is the mathematical formula for the sum of squares, but we'll take a look at what that means in a moment. Degrees of freedom, that's pretty easy to understand. It's just n minus 1, the total number of scores you have, minus 1. So if we had 10 scores in the distribution, our degrees of freedom would be 9. Sum of squares is pretty easy to calculate, but it can be somewhat tedious, particularly if you have a large data set. And then finally, we have the standard deviation. That's a term I'm going to bet that almost all of you have heard before in your life. And you might have a vague understanding of what it means. But after this lecture, we're going to know exactly what the standard deviation means. Simply put, it's just the square root of the variance, but it's a little bit more than that. We'll see how to calculate all of these in a moment. So let's start with the ranged. So the range, again, is the most crude, the simplest, let's say the most basic form or measure of variability, and it's simply the highest score minus the lowest score. So in our data set here, in this distribution, we'll find the highest score, which happens to be 98, and we'll find the lowest score, which happens to be 60. So all we have to do is take 98, subtract 60, and we have determined that this distribution has a range of 39. So what does that mean exactly? Well, think about how we calculated the range. We took the highest score and we took the lowest score, and we just subtracted the lowest score from the highest score. So what did we calculate? Well, we determined how many scores in our distribution exist between the highest score and the lowest score. And that's exactly what the range is telling us. Again, not all that useful, right? It can be useful in some instances, but you'll see in a moment that we have better or more informative measures of variability there. But range, again, is just telling us how many scores exist between our lowest score and our highest score. So in this distribution, it's 39. Again, range is a pretty crude measure of variability. Doesn't really give us a whole lot of information to work with here. Okay, so another way to think about variability, particularly when we get into variance and standard deviation, is to think about variability as a measure of, on average, how far is each score in your distribution. On average, how far is each score away from the mean? Okay, so what we can do is take our distribution, all of our x scores right there, and I made it simple for us. I calculated the mean. So in the first column here, we have all of our scores in this distribution that we just saw. And I calculated the mean, which is 79.55, and I just went ahead and put that into the second column, just for illustrative purposes. Now, if we think about variability as, on average, how far is each score from the mean? Okay, so that should be pretty easy to calculate, right? All we have to do is find out how far away each score is from the mean, and then just get the average of those distances, and bam, done, right? Then we've calculated the average of how far away each score is. So let's go ahead and do that. Let's create another column here that we call deviation scores. And deviation scores are simply how far away is each score from the mean of the distribution. So we'll start with 60, and we'll take the x score and subtract out the mean, and we end up with negative 19.55. So this is a deviation score. What does it say? Well, it says that x is 19.55 scores away from the mean of the distribution. Pretty simple, right? All we're doing is taking x, each value, and subtracting the mean. So let's do that for 62, or an x score. So we take 62, subtract out the mean of 79.55, and we find out that 62 is 17.55 scores below the mean, right? So we get negative 17.55. So we could do this for every score. We could find out how far away is each score from the mean of the distribution. So let's go ahead and do that. 65 is 14.55 score or points or values below the mean, so on and so forth. Let's keep going, right? Once we get to values that exist above the mean, we're going to start getting values that are positive for our deviation scores. So by the time we get to 96 and we subtract out the mean, we can determine, or we've calculated, that 96 is 16.45 scores or value points above the mean, right? And we can do this for each one of our values there. Okay, so we took all of our x values, we subtracted out the mean, and we calculated deviation scores. Now, if what we really are interested in knowing is, on average, how far away is each score from the distribution mean, we should be able to just take all of these values right here, add them up, and then divide by the number of scores we got. We should be able to just get the average of the deviation scores. So why not? Let's go ahead and try to do that. Oh shit, that's not good. What happened? How come I have 0 when I try to add these up? Well, this is why life is never as easy as it may seem, right? Because that's really what I want to do. I really just, the best value or the best measure of variability is for me to just get an average of how much each score varies from the mean. So I calculated all these deviation scores. I just want to get an average of those deviation scores. That's all I want to do. But we have a problem here. Whenever you try to add up deviation scores in a distribution, you're always going to end up with 0. Why? Because all of these negative values are going to cancel out all of those positive values. So you're always going to end up with 0. So you might say, okay, well, nothing I can do here. Let me just pack up my bags and go. Well, not so fast. There is something we can do to get rid of that 0. And that is we can get a transformation of these deviation scores. So we could get rid of those negatives. The negatives are canceling out the positives. So let's get rid of the negative scores. How can we do that? Well, an easy way of doing that is to square these deviation scores. So we already calculated the deviation scores, so we got them, but we're going to square these scores so we can get rid of those negative values. So we're going to create this new column over here, which is x minus the mean squared. So let's start with our first value, negative 19.55. When we square that, we get 382.20, right? So what we're going to do in this new column is simply take each of our deviation scores and square them. So our value of negative 17.55 becomes a 308, so on and so forth. We're just going to go down the line in this new column here. Okay, so let's keep going, just squaring, not particularly difficult math here. Don't do this by hand. Have a calculator, and you'll see once we actually run data or run analyses in JASP or SPSS or even in Excel, the computer will calculate everything we're trying to do in a millisecond. So right now, what I just did, just to remind you, is let's just go through this whole chart one more time, right? So I started off with my x values, so each value, each score that appears in my distribution. I calculated the mean, and I put a column in here of the mean, just so we can follow along, make it easier to visualize here. Then I created a column of deviation scores. So I took my x score and I subtracted out the mean. And that's what is in this column here. Now what I want to do is get an average of these deviation scores and use that as my measure of variability, because that's perfect. It's saying on average how far away is each score from the mean. That's a great measure of variability. The problem is you can't add up deviation scores. You're always going to end up with 0, right? But I'm not giving up hope. I'm still going to get that average, right? So what do I have to do? Well, I need to transform the scores, and I'm going to do that by squaring them. And that's what this last column is. These are my deviation scores squared. Now I can add these up because there are no negatives in there. These values are not going to cancel each other out. So I can add up those these new squared values, right? So this result that we just calculated has a special name. It's called the sum of squares. Okay? So keep that in mind. Jot that down in your notes. This value here is a very important value. So the sums of squares. And in this case, it's 2,942.7. Now, if you remember, just remember, make sure to write this down. So the sum of those squared deviation scores is called the sum of squares. Okay, now you might remember the formula for variance. I said it was the sum of squares divided by degrees of freedom. Well, I was talking about a sample, the sample variance there, which is what we're going to mostly be using in this class. Again, this is a statistics class, so we're using data that come from samples, largely. But to calculate population variance, we would take the sum of squares that we just calculated, and we would divide by the total number of scores that we have. But we're rarely going to be using population or data that comes from a population. Again, we're going to be dealing with statistics, so we're going to be dealing with data that come from samples. And in this case, to calculate sample variance, we're going to take the sum of squares, that same value that we just calculated, and we're going to divide by what is called degrees of freedom. And degrees of freedom is your total number of scores minus 1. And we're going to find out in a minute here, why do we do that? Why do we divide by n minus 1 for sample variance rather than just n? I'll give you a hint. It has to do with what we spoke about in our first lecture regarding sampling bias. If the population variance, remember, if we're calculating descriptives, parameters for a population, then we have every single person of interest. We have data on every single person we're interested in studying. But with the sample, we have to take a smaller group of people from our population. And that smaller group of people are supposed to represent that bigger population. So instead of dividing by n, we divide by n minus 1 as a way to help account for some of the error that might have happened. Well, not might have, that almost definitely happened when we collected our sample. So dividing by n minus 1 is actually going to make your sample variance higher than it would be if you only divided by n. So essentially what we're doing is padding our statistic here. So we're padding our variance. We're making it a little bigger to account for any problems that might have happened during the sampling procedure or during the sampling method process. Another way to think about this in kind of real life terms, just imagine you're at a diner or you're at a bar or something, and everyone's kind of buying rounds for each other. No one's really keeping 100% tab on who's paying for what or who drank what or who's ordered what. But it's your turn to, it's your time to leave, essentially. So in your head, you might say, okay, well, I had this, I had that, I had this, but, a little tipsy here, or, kind of getting into a food coma with all the food that I ate. So, I think my total was about $20, but I'm just going to put in 25 just to be sure, just to make sure that I covered my tab. So that's essentially what we're doing when we divide by n minus 1. We make the variance score a little bit bigger to help cover our asses, essentially, because it's likely that the sample variance that we get is not going to be 100% accurate in terms of representing the population variance. So we're just going to throw in a couple extra bucks. We're going to make that value a little bigger, just to make sure that we covered all of our bases. Because what happens if you're one of those friends who consistently, underestimates how much they owe? you stop getting invited out, right? So it's much better to be safe and just throw in a few extra bucks. So let's see this in action. The population variance, again, this term up here, let's break it down. I'm not sure if I did that exactly here, but we have the summation sign. So the sum of x scores minus the mean squared. So what does that sound like? That's the formula for sums of squares, right? So we're going to sum up our squared deviation scores. And for population variance, we divide by n. Okay? Because population variance, this means you were there with a pen and a notepad, and you were keeping exact tabs on you got every item and the price and the tax, bam, 100%. Because with the population, we're dealing with every single person that we're interested in studying. In sample, especially if we're only getting a couple hundred people to represent a sample that might be made up of millions or tens of millions of people. Chances are we're going to miss some stuff. Chances are we're going to have some error between the values that we get using our sample and what actually exists in the population. So we're not using one of these to keep track of what we're ordering at the diner or at the bar. We're trying to keep track of it in our head, and it's likely we might miss something. So it's better to be safe. So we're going to calculate population variance just so we can see what happens when we calculate sample variance using the same exact sums of squares. The only thing that's going to be different is that instead of dividing by n, when we calculate the sample variance, we'll be dividing by n minus 1. So let's just see what happens. To calculate population variance, we take our sums of squares and we divide by n, and we get a population variance of 267.52. Okay, so let's see what happens when we take the same sums of squares and divide by degrees of freedom. So again, population variance, sums of squares, divided by degrees of freedom, or n minus 1. So instead of dividing 2,942.70 by 11, we're going to divide that value by 10, n minus 1, and see what happens. Okay, so now we get a sample variance of 294.27. You see what we did there? Take a look at these two values, right? Sample variance is much lower than population variance is lower than our sample variance. What did we do? Well, by dividing by n minus 1, we inflated the variance a little bit. We threw in a couple extra bucks just to make sure we got our tab covered, right? So we do this, we divide by n minus 1 when we're using samples, because we recognize that, there's probably going to be some discrepancies between what we find in our sample and what actually exists in the population because of sampling error, sampling bias, right? As I said, the sample variance is slightly higher than the population variance, and this is to help account for errors in the sampling process. So remember, as scientists, it's better for us to err on the side of caution. And again, when going out with friends, it's better to pay too much towards your share than too little towards your share. So the same goes for science or statistical analyses here. Okay, so because we had to, now let me actually hold on. I'm going to pause really quick because I hear my dog barking to go out. I'll be right. Okay. So, as I was saying, because we had to square our deviation scores in order to calculate variance, variance is not typically used as a descriptive statistic. Why? Because it's more difficult to interpret. What we were just interested in calculating was, on average, how far away is each score from the mean. But we weren't able to do that because when you add deviation scores, you end up with 0. So we had to square it in order to calculate this thing we want to get. So essentially what we have to do now is unsquare those values. How do we do that? Because what we're really interested in is something called the standard deviation. And think of the name, standard deviation, right? Also think of it as average deviation, right? Or the mean deviation. On average, how much does each score differ from the mean? Okay, variance is simply the standard deviation squared, because we had to square all those deviation scores. So let's unsquare them, and then if we unsquare them, we could get the value that we are really after, which is the standard deviation, right? So the standard deviation is simply the square root of variance. Pretty easy to do, right? So as I said, it's not complicated math that we have to do. Just calculating variance is something you have to do in order to get standard deviation. So variance is often not used as a measure or as a descriptive statistic of variability because it's more confusing. If I asked you, how old are you? And you said, I'm the square root of 441. I'd say, okay, I don't have a calculator on me. Can you just tell me how old you are, right? But I want to know your age, which in this case, if I did take the square root of 441, I'd get 21. So let's say you're 21 years old, but you're one of those annoying people, hipsters or some, who go around saying, oh, I'm going to be the square root of 441 on Monday or something. People might say, that's great. Can you just tell us what your name is or what your age is? And that's kind of where we are with variance and standard deviation. We want to know the age. We want you to tell us 21, right? But you're telling us square root of 441. So the last step with variance, in order to get standard deviation, is to simply take the square root of variance. Even though I said variance is not used as a method, as a descriptive method, for the same reason we don't go around saying my age is the square root of 441. It's annoying. It's not really helpful to us. But you're going to see later on in the semester that variance is actually very important because it's used to calculate various other statistics. So particularly ANOVA. So as the name suggests, in ANOVA, it's an analysis of variance. So variance is going to come back. It's going to be important to understand this concept. But we're really interested in a descriptive statistic of variability that we can present anytime we present the mean. We could present the mean and then a standard deviation. So we could say, here's the mathematical average of a distribution, and here's how much on average each score differs from this mean that I just gave you. So let's go ahead and do that, right? So standard deviation, it's for a population. Standard deviation, it's just the square root of population variance. So in our example before, we had a population variance of 267.52. This would give us a standard deviation of 16.36. Okay, so this is for a population standard deviation. We work with samples largely, and certainly in this class, largely we'll be working with samples. So to calculate the sample standard deviation, we'll take the square root of our sample variance. What's the difference between population variance and sample variance? Population variance, we take the sum of squares and divide by n. Sample variance, we take the sum of squares and divide by n minus 1. Okay? One thing to note here is the different symbols that are used to denote population standard deviation and population variance, and sample standard deviation and sample variance. So our sample variance was 294.27. So getting the square root of our sample variance, we get a standard deviation of 17.15. So you see again the difference between these two values. Like the sample variance, the sample standard deviation is slightly higher than the population standard deviation. And again, this is to help account for error that likely exists in the sampling process. So this is tossing in a few extra bucks to make sure that you covered everything on your bill. So what does standard deviation tell us? It's saying on average each score is 17.15 points or values away from the mean in my sample distribution here. So let's see. When we again present a mean, we should always include the standard deviation as well. And an example of this might be the mean score for the class was 79.55, and then in parentheses SD, we'll see that's also denotes standard deviation, mostly in publications when we write our results in APA format. So our mean was 79.55 with the standard deviation of 17.15, right? 0.15. So our mean was 79.55, and on average, each score in the distribution differed from the mean by 17.15 points. That's going to be important once we, not just when we present means, we also want to present a measure of variability for the distribution, but the notion of standard distribution and mean is going to be important when we discuss the normal distribution and z-scores, which we'll do in a moment here. So, standard deviation in summary. The standard deviation gives us an average of how much each score deviates from the mean. It's the most useful measure of variability. So because the sum of deviation scores will always equal 0, we have to square each of those deviation scores to eliminate those negative values. And in the process of doing that, we calculate something that's called variance, which is simply the standard deviation squared. So the standard deviation and variance are just transformations of each other. Variance is standard deviation squared. Standard deviation is square root of variance. So to undo the squaring of our deviation scores, because we only squared them to get rid of those negative values, to undo the squaring, we take the square root of the variance to calculate standard deviation, which is what we wanted all along. Okay? Again, variance is not typically used as a descriptive statistic of variability. However, it is used in calculating other statistics that we will discuss later on in the semester. Okay, so standard deviation in summary. Okay, this is just another slide. I was like, did I have a duplicate in here? As I just said, here's an illustration, or I have it written out. The standard deviation and variance are just transformations of each other. So standard deviation will equal the square root of variance, and variance is simply standard deviation squared. They're just transformations. You could go back and forth with standard deviation and variance. Population variance is denoted by omega squared. Sample variance is denoted by a lowercase italicized s squared. Population standard deviation denoted by the symbol omega, and the sample standard deviation is denoted by the symbol s, just a lowercase italicized s. Again, sometimes when you see results in a article or publication, standard deviation might be denoted by SD, but this is the mathematical symbol used. Okay, z-scores. What should I do here? I'm going to make this into a part 2. So you can digest the material for central tendency and standard deviation, and I'll see you back here in a hot second. We'll do this as a two-parter.